Semiconductors.
Okay.
Now we're going to start on something very important, something called semiconductors. Semiconductors are parts like diodes and transistors. Semiconductors are what we commonly refer to as the active components in a circuit. The semiconductors are the parts that switch on and off to control the flow of electric current. They're actively switching on and off, sometimes letting the electric current through, sometimes shutting it off. This is different than a resistor. A resistor is what we call a passive component. A resistor just sits there and resists. It doesn't actually switch on and off or anything, where a diode and a transistor will. And as a result, since semiconductors are the things that are actively switching on and off in a circuit, they fail fairly often. Other than capacitor failures, diodes and transistors are really the most common types of failures that we have. Again, capacitor failures because the electrolyte dries out, but semiconductors fail because they are working very hard, switching on and off, controlling the flow of electric current. The first semiconductor that we're going to look at is a part called a diode. And those things that I've given you are diodes. The schematic symbol for the diode looks like this. Now, on the schematic diagram, you will actually see this filled in solid black. I won't do it on the board because it's a big hassle with the whiteboard and the marker, but it's actually filled in solid black. It's got this bar at this end like this. The diode comes from the Greek word, the name diode comes from the Greek word di, meaning two, and ode, like electrode, two leads. Two leads. A diode is simply a semiconductor that has two leads. And we have names for these two leads. The lead on the left is called the anode, A-N-O-D-E. And the lead on the right is called the cathode, C-A-T-H-O-D-E, cathode, the anode and the cathode. If you need a way to remember which lead is which, you can remember it the way my good buddy Nathan Bush from Dallas, Texas remembers it. He's got a girlfriend named Kathy, but she's kind of a wino, and you can always find her at the bar. So the cathode is the bar end. Kathy at the bar, get it? Cathode bar, anyway. And if you look at the diode that I gave you, diodes that I gave you, you'll see a ring or a stripe on one end. Obviously, that's the cathode end. And the other end's the anode. The reason that it's important to know which lead is which is that the diode is a one-way gate for electric current. According to the schematic diagram and according to the way we think of electric current flowing, conventional current from positive to negative, electric current only flows through the diode if it's going the same direction the arrow points, which makes a lot of sense. The current will only go through the diode in that direction. It won't go back again. It won't go back the other way. It only goes through one direction. Let me put this diode in a demonstration circuit for you and show you how it works. This is just a demonstration circuit that shows you how the diode works. This does not have any function whatsoever. This doesn't do anything. But let's go back to the schematic diagram that we've seen several times already with the battery and the lamp like this. And there's our complete circuit. Everybody with me so far? We went through this before. I'm going to break the circuit right here. And I'm going to put a diode in series with the battery and the lamp. Remember, in a series circuit, anytime the electric current has to go through one part to get to another part, they are in series. All right, well, if I connect this circuit now, do you suppose this lamp should be on, will be on or off? Should definitely be on, sure. Okay, so let's connect this guy up here. And I have the red wires connected to the positive side of the battery. And it goes from there to the diode. Which side will it connect to, the anode or the cathode?
Anode.
Anode end, right? And I'll use this really bitchin' yellow wire here, amarillo, to connect to the cathode. And then the other end of the cathode goes to the lamp, and if we're correct, this should light up. Ooh, ah, all right, so it's lighting up. If I reverse the diode, it should not light up. So I'm just going to disconnect the diode here and just turn it around. If the diode's good, ooh, not so impressive when it doesn't light up, all right? And, of course, now, what we had first when it was conducting is, of course, service call, radiation leak, Sector 5, all blue personnel to the shelters immediately. All right, so when it was running, of course, the current was going this way. Is it going the same direction as the arrow? Yes, it is. It's conducting. Then I reverse the diode. When I turn the diode around like this, remember the current still wants to go from positive to negative. We haven't changed that. But the diode's like this. It's going, hey, no way, Jack. You're not going through me. Forget it. And it's blocking it. Now, without touching the diode at all, how do you suppose I could change this circuit around to make the light bulb light up?
Change the battery.
Get a new battery?
Reverse
reverse the connections on the battery. Sure. If I reverse the connections of the battery, that's going to change the direction the current flows naturally. Ooh, okay, really good. There you go, it's magic. Magical. Okay, so, and now, of course, the schematic diagram looks like this. We've turned the battery around. That's the negative now. There's the positive side. Now current goes this direction. Now this is the source path, isn't it? We turn the battery around. Return path. Hey, go in the same direction. Shit, it's on. It's going the same direction. It's on, period. So you'll notice, too, that it didn't matter whether I put the diode in the source path or the return path. As long as it's going the right way, it'll conduct. Now, again, this is just a demonstration circuit. This is just to show you how the diode works. But one of the places we use a diode a lot is to change alternating current into direct current. Remember that alternating current sometimes goes this direction, then it goes this direction. It's constantly changing direction, one direction, then the other. Well, we take that AC and we run it through the diode, and here's what happens. The diode lets it go one way, but keeps it from going back. It can't go back. The diode allows it to go one direction, but it can't go back through the diode. Is it working? Yeah, it's working. Okay, it can't go back. Everybody's watching the camera. It can't go back. It keeps the current going in just one direction, and that's the definition of DC, isn't it? Remember I said current that just goes in one direction is DC. So we use diodes to change AC into DC. Turn in your blue book to page R5. The process of changing alternating current into direct current is called rectification. The process of changing AC into DC has a name. It's called rectification. Ooh, another really horribly big term. What does that mean? Well, it comes from the English word rectify. Rectify, of course, means to make something better. You got a problem, you rectify the situation. Well, our problem is AC. AC is really good for some things. It's great for motors and toasters and weed whackers and hair dryers and stuff like that. But alternating current is no good at all for electronic things. Things like computers, televisions, VCRs, radios, they all require direct current. So we rectify the problem of AC by running it through this diode and changing it into DC, a process we call rectification. We're rectifying the problem of AC being so cruddy, we turn it into DC. And in fact, a diode that's used to change AC to DC, as you see here on page R5, is called a rectifier. A diode that changes AC into DC is called a rectifier. And you see that this page, it doesn't say diodes on it. It says general purpose rectifiers. All rectifiers are diodes. All rectifiers are diodes. Now, we do have places where we use diodes not as rectifiers. Not all diodes are used as rectifiers. That is, not all diodes change AC into DC. For instance, in a pinball machine, you know that there's diodes across the flipper coils of a pinball. Those ain't changing AC into DC. Those are doing something else. I'll tell you on Saturday what those are doing. But for the most part, diodes are used to change AC into DC. And in fact, it's a real common problem on these switching regulator power supplies. Much of the time, the only thing that's wrong, and we'll do this on Wednesday, much of the time, the only thing that's wrong with your power supply is one 25-cent diode. I mean, it's very common. The last class I did, virtually half the problems were just one single diode. You'll see how simple this really is to fix. Everybody cool so far? Now, before we get into testing the diode, I really need to show you a little bit more about what's inside the diode. Inside the diode itself is made of something called silicon. Silicon Valley, here's where we are in Silicon Valley. Silicon, pure silicon is obviously one of the elements. Basically, silicon is dirt, it's sand. Pure silicon by itself is actually an insulator. Something that does not conduct electricity very well at all. It doesn't conduct electricity at all. Pure silicon is actually an insulator. The diode starts out as a single chip of silicon, a single little chip of silicon. But if it was made out of pure silicon, it would never conduct electricity at all. So they add some chemical impurities to the diode. You don't have to know this, they're called dopants. What it does is it changes the atomic structure of the silicon. They divide it into two halves. By adding these impurities as they make the diode, one side ends up with extra electrons. Remember, electrons have negative charges, don't they? If I have something that has extra electrons, that thing now has a negative charge. In fact, this silicon is known as type N silicon, N for negative, obviously. The other half of the little chip of silicon has electrons taken away from it. Pretty weird deal. Through a chemical process, they actually strip some of the electrons out. By taking some of the negatively charged electrons away from one side, it turns it into a positively charged piece of silicon. I mean, naturally, if you have something that has the same number of positive and negative charges, and then you remove some of the negative charges, what's left is more positive than negative. And we call this type P silicon. P for positive. So we have this silicon chip that's made out of type P silicon and type N silicon. Now really, in your little diode, it really looks like this. It's a little wafer, a little disc. And it's divided in half like this with type P on one side and type N on the other. Here's the component leads attached to the silicon, and then they cover the whole thing with epoxy plastic. That's what your thing looks like inside. In fact, if you see one of these broken in half, as you will probably see eventually in your life, you can actually see the little chip of silicon inside. Or if you take a pair of dikes right now and just slice your diode in half, you'll see that it'll break right at the silicon. Anyway, so we have this diode here, and it's type P and type N. Well, remember I mentioned to you before that opposite charges attract, just like opposite poles of a magnet attract. If I put North Pole next to South Pole, they attract each other. Well, over here we've got positive charges here and negative charges there. Gosh, why don't they just kind of, come together and neutralize each other? They're opposite polarities. Well, here's why not, and this is important. If you've been asleep until now, wake up. Because right here, where the type N and the type P, or the type P and the type N silicon meet, we have a really important thing that you just got to know about, and it's something called the PN junction. The PN junction acts like a barrier and keeps the type P separate from the type N. It's kind of like a little brick wall in there, although it isn't really anything at all. It's like a little barrier that keeps the type P separate from the type N. Now, I think what really happens in this area, and I'm not a physicist by any means. Like I said, I'm a high school graduate, and that's all. But I think a little bit of the electrons and the positive charges kind of do mix together a little bit and form a kind of a neutral, like a little Switzerland in there in between France and Germany, kind of. But the important thing is to know that the PN junction exists. That is, it's a barrier that keeps the P separate from the N. The reason it's important is that when we test diodes, and as you'll see later on when we test transistors and even integrated circuits, what we're going to do is test this PN junction and see if it is working properly or not. Now, of course, I'm going to tell you how to do that in just a few minutes. But this PN junction is real important. It's where the type P silicon meets the type N silicon. Let's put this diode in our demonstration circuit and see how it works. Whether or not you understand how it works is not terribly important. I think it's fascinating how this thing works, and I'm going to explain it to you. If how it works doesn't make sense to you, that's okie dokie, because I'm going to show you how to test it in just a second. But right now, the diode is facing this direction. So I'm going to put it in the circuit that we had before, with the battery, the diode, the lamp, and according to y'all, this should be on right now. So here it is. There's the battery. There's the lamp. Is everybody with me so far? This is pretty simple. And it should be on now. Well, let's see what happens. Remember that similar charges repel each other. Again, just like with magnets, if I try to put two south poles together, they'll repel each other. And it's the same thing here. Here I have the positive charges in the type P silicon. These have a nickname, by the way. These positive charges are called holes. They're called holes because essentially it's like an atom with a hole in the electron shell waiting for an electron to fall into it, basically. So they're given the nickname holes. These holes can move around inside the silicon crystal. So can the electrons. The electrons can move around too. So here we have the positive charge of the battery, the positive side of the battery, connected to these positively charged holes, and it's going to push them that way, isn't it? It's going to repel them. What it really does is it literally slams them up against the PN junction. Over here, here's the negative side of the battery connected through the lamp to these electrons. Negative battery, negative electrons, same thing, it's going to repel. And the same thing happens. It pushes the electrons up against the PN junction here. Well, in this case, what happens is the pressure from the battery literally forces the electrons into those holes. Remember, voltage is pressure. The pressure, the voltage from the battery, literally shoves the electrons into the holes. What it does is, because we've got electrons on this side pushing against the PN junction and holes on that side pushing on the PN junction goes away. Now, it doesn't destroy itself. It isn't like instantly gone or anything. As soon as I remove the power, that PN junction will pop right back up again. But essentially, it's just like pushes it aside. There's so much pressure there. It's like, you know, if I close this door here and I try to hold it, if one person's pushing on the, well, if there was a door, if one person's pushing on the door, I can probably hold it. But if I've got enough people pushing on the door, you're going to push through. Same thing here. If there's enough pressure, enough voltage, and it doesn't take very much, the electrons in the holes pushing on that door, on that PN junction, literally knock it aside, and the diode starts to conduct. Well, I don't think that part's that interesting. Okay, it does that. Great, wonderful. But what I think is interesting is the other way around. Let me put this back together again. Here's the positive charges. Remember, that's the type P silicon. the p-n junction, here's the electrons in the type N silicon. Let's turn the battery around. If I turn the battery around, is this thing conducting or not?
No.
Negativo, not. Okay. This is pretty cool. Remember, opposite charges attract each other. Here's the negative side of the battery connected to the positive charges. It's going to suck them this way, isn't it? Away from the p-n junction. Positive, positive, away from the p-n junction. Here's the positive side of the battery connected to the electrons. Same thing, it's going to suck them away from the p-n junction. Well, now not only do we not have the electrons in the holes pushing together at the p-n junction, but we're left with an area here and an area here that's made out of pure silicon. What do we know about silicon? Doesn't conduct. It's an insulator. That's why it doesn't conduct the other direction. That's why these things are called semiconductors. They're called semiconductors because sometimes they conduct. They sometimes conduct. Sometimes conduct. Semiconductors. They're not called semiconductors because, oh, well, they kind of conduct, but they do a real shitty job of it. You know, but that's how it was explained to me at one time. It's like, well, you know, they kind of conduct, but they really don't do that good a job. Well, that's nonsense. Look, this thing is on. It's on. This light bulb is definitely on. There's no question about it. And yet, when I reverse the diode, it's completely off. It's completely off or it's completely on. One or the other. So it isn't like it does a lousy job of conducting. When it's conducting, it's doing a great job. So that's why these things are called semiconductors, because they sometimes conduct. Does that make sense so far? Now, it does take a certain amount of pressure, a certain amount of voltage to operate that p-n junction. Let me just redraw this here. Let's go back to our original circuit here. Here's the battery, the diode in series with the lamp, like this. And let's say we have a 6-volt battery, as I do here. Of course, that means that the voltage right here is 6 volts. That makes sense, doesn't it? In fact, believe it or not, there's a law of electronics that states that the voltage along a wire is the same everywhere along a wire. No shit. I mean, if you jump start a car, don't you expect the 12 volts at the battery to end up at the other end of the jumper cables? But there's a law. It says the voltage on a wire is the same everywhere. So it's 6 volts coming out of the battery. Of course, it's 6 volts right there, too. Everybody with me there? On the other side of the diode, it'll actually be only 5.3 volts or so. It takes a certain amount of voltage to operate that p-n junction. It takes approximately 0.7 of a volt to operate that p-n junction, to push the junction aside and allow the diode to conduct. That 0.7 of a volt is actually used up inside the diode, and we give it a name, and it's a real important term. It's what all this has been leading to. It's something called the junction drop. And what I mean by junction drop is the voltage that is dropped or lost across a perfectly normal working p-n junction. And I can show this junction drop to you. Watch the lamp. As I short the diode out, you'll see that the lamp will get just the tiniest bit brighter. I'm just shorting the diode here. You can see it gets a little bit brighter. What I'm doing is by shorting the diode, I'm just eliminating that junction drop. So it does take approximately 0.7 of a volt to activate the diode and to allow it to conduct. Now, we don't have to worry about the fact that that 0.7 of a volt is used up. If an engineer has put a diode in a circuit, he knows that that 0.7 of a volt is going to be used up. That isn't a problem. In fact, we use that to our advantage, because when we test the diode, what we're actually going to be testing is the junction drop to see if the diode's working properly or not. And I'll show you in just one second. Now, when I say it takes 7/10 of a volt to operate the junction, to operate the diode, 7/10 of a volt is used up across it, that's really an average reading. It will be somewhere between, usually, 0.5, a half a volt, to 9/10 of a volt. Obviously, 7/10 is exactly right in between. 7/10 of a volt is the term the engineers use when they're talking about what we call the junction drop of a silicon diode, 7/10. But it'll be somewhere between 0.5 and 0.9, depending on the size of the part. A bigger part, physically a larger part, will have a lower junction drop than a smaller part. The smaller the part is, the physically smaller it is, the higher that junction drop will be. Now, let me show you what the hell I'm talking about here. Because here's how you test the diode. Your meter should have a diode test setting on it. Your meter should have a diode test range on it. If your meter does not have this little diode test setting on it, you need to get another meter. I'm serious. You need to get a meter that has this test on it. It's the single most important thing you can have on your meter. And here's how you test the diode. With the meter set on the diode test range, and you can touch your fingers to the meter leads, no problem with this test. With the black meter lead with the red lead on the anode and the black lead on the cathode, your meter should show you a junction drop. And from now on, for the rest of my life, when I say junction drop, I'm saying something between 0.5 and 0.9, usually. Now, if your meter says something else, if it says something a little lower than 0.5, that's probably okay. Fluke meters have a tendency to show a little bit lower than 0.5. In this case, the meter says 0.586. When I reverse the diode, the meter says open, OL, like I'm not touching anything at all. Well, obviously, if I get a reading one direction and nothing the other, the diode's working like a one-way gate, isn't it? I'm getting something one direction, and I don't care what it is even, and I'm getting nothing the other direction, the diode's working like a one-way gate. But not only am I getting something in one direction, but it's the correct number. It's something between 0.5 and 0.9. This is the really cool thing about having a meter with a diode test setting. Obviously, there's a battery inside the meter. The battery sends the juice through the wires, the leads of the meter, and actually measures the amount of voltage that is dropped across the PN junction, the junction drop. Heck, it's almost like having an X-ray. Now, here's the little teeny diode. It says 0.584. If I go to the larger diode, it should show me something somewhat lower. It says 0.53. The larger it is, the lower that will be. Even if this read 0.49 or 0.48 or even 0.45, as long as it reads open when I reverse the leads, it is good. Right? Everybody try testing your diodes right now. Anybody else need a meter?
Yeah, the larger one reads less.
The larger one should read less. Here's a bad diode. Meter set on the diode test setting. First of all, my meter beeps at me, and the meter says 0.000 right now. Let me just zoom in here for the folks at home. Right now, I'm not faking you out. I'm not touching my leads together. 0.000, and of course it reads the same both ways. What's wrong with this diode? No, it's shorted. It's the opposite of open. Look, if you touch your two meter leads together, do it right now. Look at this. Touch your leads together. Beep. You see what your meter says? 0.000 probably. That's what diodes do when they fail. 999 times out of 100, when a diode goes bad, it is dead short. That's why it's so easy to find these things in circuit even. When a diode goes bad, even if it's in circuit, it's usually no question about it. It is dead short. And of course it's shorted both directions. If you look at page R5, we see all these different rectifiers, diodes, rectifiers. Let's take a look at the two diodes that you have. Let's take a look at the small one first. What is the part number on that the smaller of the two diodes?
1N4004.
Right. It's a 1 and not an I. It's a 1N4004. A very common part. I think almost everybody is familiar with the part. We use it all over the place in games. Very common part. The 1, by the way, the first number 1, happens to indicate, you don't have to know this, the number of PN junctions in the device. The number of PN junctions. You'll see the diodes start with the number 1. Later on, we'll look at transistors. They have 2 PN junctions. They start with the number 2 very often. Can you get that for me? Thanks. All right. Well, diodes have two different specifications. Like all of our components have different specs. Diodes have two different specifications. One is the voltage rating of the diode. The voltage rating of the diode is the maximum amount of voltage that the diode can block. It's the maximum amount of voltage that the diode can block. In other words, remember, half the time the diode's going to be conducting and half the time it isn't. When it's not conducting, it's blocking the voltage, blocking the current flow, I should say. How much pressure can it handle? How much voltage can it handle? The voltage rating of a diode, though, is not, it doesn't say diode voltage or anything like that. If you go to a store to get a diode, it doesn't say, hey man, I'm a 400 volt diode or whatever. The voltage rating of a diode is listed as the diode's peak reverse voltage. Peak reverse voltage, or PRV for short. When a diode is reversed, it's blocking. That's what reverse means. The hotshots refer to this as a reverse bias. You don't have to know that. When a diode is off, they call it reverse biased. You don't have to know that. But this is the peak, the maximum amount of voltage that the diode can block when it's trying to go the wrong direction. In other words, if the current's trying to go through this direction, the diode's going, stay away, block, block, block. I can handle, let's say it's a 100 volt diode. I can block 50 volts, I can block 75, I'm blocking 100, I'm blocking 100. But you put 200 volts on it, it's going to blow it away. The pressure's just going to blow it away. So, the voltage rating of a diode is the maximum it can block, also referred to as the peak inverse voltage. Means exactly the same thing. It'll either be PRV or PIV. Means exactly the same thing. It's simply the voltage rating of the diode. And the other rating of a diode, the voltage rating of a diode is just like the voltage rating of a capacitor. It's the maximum amount that it can handle. It's not how much it puts out, it's the maximum it can handle. The second rating for a diode is the current rating. The current rating is the maximum amount of current that the diode can pass through itself. In other words, when the diode is conducting and current's going through it in the proper direction, how much current can the thing handle? Can it handle 1 amp? Can it handle 2 amps? Can it handle 3 amps? Can it handle 4 amps? How much current can the thing actually handle? Well, believe it or not, we use the letter I to denote current. I know that seems incredibly stupid, but we do. We use the letter I to denote current. And the reason that we use the letter I to denote current is that early pioneers in electricity, early engineers, thought of current as intensity. That is, the more current they had going through the circuit, the more intense the spark was, the more intense the shock was when they touched it and shocked the shit out of themselves, the more intense whatever it was. So although you would think we would use the letter C for current, we don't. I means current. And the current rating of a diode is listed as I with a little O underneath it. I sub O is what they would say. This little letter is what's commonly called a subscript. And they use this in technical jazz all the time. A subscript, the subscript just further describes what we mean by the big letter. In other words, I means current. Well, what kind of current, wise guy? Well, output current is what that means. The output current. And the diode, the output of a diode is called I sub O, the output current rating of the diode. And that is the maximum amount of current it can pass through itself. All right, well, let's look this up. If you look on page R5, and you look down this far left-hand column here, 1N400 series, the 400 series, what is the voltage rating of the 1N4004? Sure, 400 volts. Meaning that I can use this in any circuit up to 400 volts. What's the current rating? Look at the top of the page. You see where it says I sub O, average rectified forward current in amperes. What's the current rating? 1 amp. So this is a 400 volt, 1 amp diode, meaning it can be used in any circuit up to 400 volts, any circuit up to 1 amp. Let's take a look at the other diode, the big diode I gave you. What's the part number on that thing? 1N5404, correcto. 1N, and again, it is a 1 and not an I, 5404. What's the voltage rating of this guy? It's also 400 volts, and the current rating? 3 amps. Well, here's the really cool thing about diodes. When you're working with diodes, if you need to substitute a diode, you can always use another diode of the same or higher voltage, the same or higher current. You can always go up in voltage rating. You can always go up in current rating. For example, another common part that you might see, another common diode that you might see in many different places is a 1N4001. What's the voltage rating of that guy? That's only a 50 volt diode, isn't it? If I have a 1N4001 and it's bad, I can use a 1N4004 as a substitution. No problem. What I'm saying to you is, you get to a location, you find a bad diode because it's shorted. You look at the number, it's a 1N4001. Shit, all I got is 1N4004s, and I got to go to Radio Shack. Well, you don't. You can use the 4004. You can go as high as you want. In fact, if you look on the list, 1N4007s, those are 1,000 volt diodes. Those are pretty common, easy to get diodes. And in fact, the place I usually get my diodes from, they're the same price as the 4004s. And so very often I'll buy 4007s because I can use them for anything, can't I? Up to 1,000 volts. So, again, my point is, if you have a diode, it's only a 50 or 100 volt diode or something, and you've got a 400 volt diode, you can use that as a substitute. And you can also go up in current rating. As long as the voltage is adequate, you can go up in current rating as well. So for instance, if I have a 1N4004 and it's bad, can I use the 5404 as a substitute? Absolutely. Only problem, look at the size of the leads. You see how fat the wire leads are on the 3 amp diode, the 1N5404. The component leads are very, very fat, and you may not be able to get them in the hole. Rather than make a big hole in the board, if you ever have to do this, and I seriously doubt you will, but here's what I do. Here's the printed circuit board. Here's the old diode. Soldered. It's soldered under the board. And as Jeff said earlier, clip off those wires when they solder stuff in. What I do is I clip the body of the old diode out, leaving the wires sticking out like that. Then I mount my big, humongous, fat diode on here with the big fat wires and just solder them on like that. Otherwise, you'll try to ream out the board and make a hole big enough for the diode, and it'll butcher the board. I've only had to do this like twice in 20 years, so I don't think you'll ever have to do it. But anyway, so you can always go up in voltage, you can always go up in current, or both, as high as you want. Okay, everybody cool on that? Diodes, there's no question at all about checking diodes. Like I said, most of the time you can test them in circuit. Generally, my philosophy regarding checking parts in circuit, that is, as they're mounted on the boards themselves, is that I always try checking everything in circuit. Try checking it in circuit first. If it seems like it's bad, you're going to take it out to replace it. When you get it out, double check it. When in doubt, pull it out. Basically, if you're checking a part in circuit and it checks a little weird, you don't know what the hell's going on, unsolder it, take it out of circuit. We often need to have 4 diodes connected together in a circuit like this. You don't really have to draw this in your schematic diagram. You can if you want. On your notes, I should say. We'll be going over this a bunch. This is called a bridge rectifier. Although you see in the page in front of you it's called a rectifier bridge, but most people call it a bridge rectifier. A bridge rectifier is simply 4 diodes connected in a circuit like this. A bridge rectifier may be made of 4 individual diodes, or it can be 4 in a one-piece package. The cool thing about a bridge rectifier, and we use these in power supplies exclusively, really, is that you put alternating current into these 2 leads, and you get DC, negative and positive, out the other 2 leads. Mira. Here's typical bridge rectifier. You see the 4 legs on the bottom of it. Just back up a little bit, focus it. And you can see here's where the AC power comes in this lead. Here's positive DC out, like that. Here's another one, and you can see the something burning.
What about
you can see the
air conditioning?
well, something really stinks. Is that what it is? Okay, if you look carefully, you can see the positive. See the little positive mark and the little squiggly AC lines? See that? On the top of this bridge?
Yeah.
Okay, the little squigglies mean AC, and then you see negative and positive. The squiggly means that's where the AC comes in. It's actually called a sine wave. We'll talk more about that tomorrow. Bridge rectifiers can look like that. They can look like this. Here you can clearly see the AC inputs in the middle, and the negative and positive, like that.
So the purpose of that is AC into DC?
Correct. Changes AC into DC. And again, what I'm doing now is introducing you to the parts. We will take a look at the actual circuits tomorrow, actually. We'll start on this. But it's very easy to test the bridge rectifier to see if it's good or bad, because all you have to do is test it as if it is 4 individual diodes. To test the bridge rectifier, you're going to check it as if it's 4 individual diodes. And again, you're going to use the diode test setting on your meter. Let me check what I believe to be a good one here. And all I'm doing here is I'm checking each. Hang on, you guys, don't do it. Just watch me for a sec, okay? Just to keep it quiet in here. What I'm going to do is check each of the 4 diodes. If anyone's bad, we'll know it in a hurry. So, start with. You can really start anywhere. It doesn't matter. Start with any lead anywhere across any diode, and I get an open reading in that direction. When I reverse the diodes, reverse the leads, I get a junction drop. Now in this case, the meter only says 0.462. I got to tell you, remember I said it's supposed to be between 0.5 and 0.9, but that's really kind of an arbitrary designation. As long as I get open one direction, which I did, and something like between maybe 0.45 really, and 0.9 was probably more like it, I'm okay. Different meters will read things differently. And remember I said the bigger it is, the lower that'll be? Well, look at the size of that sucker. That's a big bridge rectifier. So that's perfectly okay, because when I reverse the leads, I see that open reading. So that one diode is good. This diode happens to be this one. or this one. I really have no way of knowing which it is. So that one's good. Now we'll rotate it 90 degrees and check the next one. Junction drop, 0.46 it says on the meter, open. So that one's good. This one happens to be the other one of these ones. So I've checked both of those. But I can't tell which it is, really. Next one, junction drop, 0.46, open. That one's good. One more to check, open. Junction drop. So this whole bridge rectifier is good. Now I believe I have a bad one here, and we will find out in just a second here if I'm correct or not. 0.56 junction drop. Now it's smaller, isn't it? So that makes sense that it's somewhat higher. And to be quite honest with you, if I get a junction drop one way, I really don't usually bother reversing it because it's going to be open the other way. So that one's good. That diode's good. Whoops. 0.001. I'm not faking you out here. Let me just hold it up clearly so you can see that I'm not. That diode is shorted out, isn't it? That one diode is shorted out. Since you can't get in here to repair it, obviously the whole unit's bad. Let's just out of curiosity check the other diodes. Open. Junction. That diode's good. Junction drop. Open. That diode's good. So there is one bad one in here. It happens to be usually it's the positive going diode. The one that goes from AC to positive. It's that one or that one. I don't know which one it is, but it's one of those. And obviously it's bad. It's dead short. And of course you could pick that up in circuit, no sweat. This meter even beeps at you. It's going bad, bad, bad. Okay. So here's a bad one. I have one more here that's probably bad. I believe it to be bad, if I'm not mistook. This is a fairly common failure in power supplies. Not the most common by any means, but that's where these bad ones actually came from, switching power supplies. There's one. I get a junction drop, 0.6, 0.7, very small, so it makes sense. 0.7. Oh, it's even up to 0.8. Wait, it's freaking out. Wait a minute. It's really bad, or I'm just not getting my meter leads on there. Here, let's try this one here. Open one direction. Open the other direction. No, maybe I'm not. If that ever happens to you, by the way, touch your meter leads together and make sure everything is hunky-dunky. When you're working on something and nothing you're doing is giving you any voltage readings or any indication of anything, always touch your leads together to make sure that the leads are working and your meter's working. Okay, so let's try this again. Maybe this diode's worse than I thought. Junction, 0.54. Reverse your leads, open. That diode's good. See, this one's really giving me some weird readings. Now I got 0.4 on that one. That's really strange. That's pretty darn low. I get an open the other direction. I get open reading there. Open reading both ways on that one. One of these diodes is open. I'm getting an open reading both ways. The diode's open, which is pretty unusual. Usually they short circuit. That's interesting. I wonder where this one came from. So in this one of the diodes is open. That's pretty weird. But it certainly didn't pass the test. There's no question about that. So as far as diagnosing bad bridge rectifiers are concerned, it should not be a problem. It's pretty obvious. It's very unusual to have an open circuit. Almost always they short circuit, like the first one I showed you. Bridge rectifiers have the same ratings as diodes do. After all, they are just diodes inside. They're rated by voltage and by current. Same thing. You can always go up in voltage rating. You can always go up in current rating as well. Okay, make sense? All right. And now we're going to start on a quick look at transistors, and we'll finish up with transistors tomorrow. I see lots of transistor failures, especially in power supplies and monitors and pinball machines. Very common. Much of the time, if you have a problem that's not a capacitor, you have a semiconductor failure, and transistors are real common failures. I see lots and lots of transistor failures. Transistors come in a wide variety of different shapes and sizes, different packages. You have 3 of those different packages, and each package has a different designation. The giant transistor that I gave you that looks kind of like that, not exactly. It's kind of, yes, this kind of guy right here. This transistor is known as a transistor in the TO3 package. That's transistor outline number 3 is really where that came from, the TO3 package. Commonly referred to as a power transistor, but it's really just a transistor in the TO3 package. Another one that I gave you that is no doubt familiar to a lot of you that have pinball machines is this package. This is actually called the TO220 package. TO220 package. Now, you'll note the part number of this part happens to be TIP31. This TO220 package was developed by Texas Instruments. TIP, Texas Instruments package. Anytime you see a part number that starts with TIP, it's probably in this TO220 package. And then last and least is this little guy here. This is the TO92 package. This is by no means the only 3 different transistor packages that exist. There are many, there are dozens and dozens of different types of transistor packages. And we'll see a couple of more, we'll see a couple of others later on. But these are the 3 most common. The only difference between these 3 transistor packages is the amount of current the transistor can handle. All transistors work the same way. They test the same way. The only difference between these guys is how much current they can handle. The bigger it is, the more current it can handle. Like the TO3 package can handle up to about 50 amps. The TO220 only 10 amps. And the TO92 only 1 amp or so. Maximum. This is maximum for each one. But as far as testing them is concerned, as far as we're concerned, as far as the specifications and all that stuff, they all work and do exactly the same thing. Basically, a transistor is just a switch. Really, that's all a transistor is. A transistor is basically just a switch, as we'll see as we go through this thing. Now, we do have 2 different categories of transistors, 2 different polarities. Some of our transistors are known as NPN transistors. Others are called PNP transistors. Some are NPN, some are PNP. Remember how the diode was made out of the type N silicon and the type P silicon? Remember that? Well, that's what it has to do with. Where the diode was 2 different types of silicon, remember type P and type N, the transistor is like a sandwich. Like an NPN transistor has type N bread and type P bologna, basically. A PNP transistor has pumpernickel on each end and some non-specific food item in the middle, whatever that is. It starts with an N there. But that's how they get their names, NPN and PNP. And remember the diode had that 1 PN junction to test? The transistor actually has 2 that will test, and I'll show you how to do that in just a second. But because we have 2 different polarities, we do have 2 different schematic symbols for transistors. You don't have to turn there, but it's on page R1 or R2, I think it is. The NPN transistor looks like this. And you will usually see a circle drawn around these. I won't generally do it because I'm not much of an artist, as you can tell, and my circles never come out looking too good. But this is an NPN transistor. The PNP transistor schematic symbol looks basically the same, except that the arrowhead points in toward the center of the symbol instead of pointing out. It does not make any difference which way I draw the symbol. The thing that you can use to tell the difference between them is if the arrow points out, it's NPN. If it points in, it's PNP. In other words, if I take this NPN transistor and turn it 90 degrees, the schematic symbol looks like this. The arrow still points out. If I take and I flip it upside down and put the arrow on the top, it will still be pointing out. Same thing with the PNP. The reason I draw them the way I do on the schematic diagram on the board here is that is the arrow on the top here and on the bottom here, is that in a schematic diagram, electric current flows from the top of the schematic down to the bottom usually. And it flows just like through a diode, the way the arrow points, it flows through the transistor following the arrows. That's why I draw them the way I do. And you'll see more about this as we go through it. But you remember that the diode had names for the two leads. Remember the anode and the cathode. Well, the transistor leads also have names. The lead with the arrow on it is called the emitter. E-M-I-T-T-E-R, the emitter. As the name implies, it emits something, and what it emits is electrons, actually. On the same side as the emitter is the collector, collecting what's emitted by the emitter. Again, specifically, it's electrons. And then over here on the left-hand side, all by itself, is the base of the transistor. So the transistor has three leads: the emitter, the collector, and the base. PNP, same thing. The base on the left, the base, as they say in Mexico, the emisor, the emitter. No, it's actually E-R. And the collector. The emitter, the collector, and the base. Let's start off by taking a look at the NPN transistor first, because we see more NPNs than PNPs. Basically, a transistor is just a switch. That's all it is. A transistor is just a switch. Here's how it works. In a transistor, the main switch is between the collector and the emitter. The main contacts, if you will, are between the collector and the emitter. When the transistor is off, there is no connection between the collector and emitter whatsoever. None. When the transistor is turned on, the collector is connected to the emitter inside the transistor. When it's off, there's no connection between the collector and emitter. When the transistor is on, the collector is shorted to the emitter. Not shorted, destroyed, ruined, but I mean just connected inside. The base is the controlling element of the transistor. The base is the thing that controls it. All we have to do is put a small amount of voltage on the base of the transistor, and it will turn it on and connect the collector to the emitter. Gee whiz, guess how much voltage it takes on the base of the transistor to turn it on? What numbers have we used so far? 0.7. Right. Remember that 0.7? Remember I said it takes a certain amount of voltage to operate the diode, that junction drop? Same thing with transistors. That 0.7 is like a magic number that we get to again and again and again. That's 0.7 of a volt, because that's how we turn the transistor on. All I have to do is put 0.7 of a volt on the transistor, which is an itty-bitty amount of voltage, isn't it? And the collector and the emitter connect together. Here's the easiest way to think of the transistor. Think of the transistor as a wall switch like this one over here. This is the base. This is the base. The toggle, the thing that you touch, is the base. And you know that on the switch, you know, there's a couple of screws over here on the switch, right? When the transistor is off, there's no connection between those two screws at all. That's like the collector and the emitter of the transistor. It'll come off. I did this once. I had the wrong kind of pen. I had one of those marks a lot that don't come off. But the base is like the toggle. Does it take very much energy for me to do this? No. It takes very little effort to hit the toggle, the switch. And yet when these two screws on the side are connected together, just like the collector and emitter, I can be controlling thousands of watts of power. Not just the insignificant little light here, but I can be controlling a lot of power that way. So it's the same thing with transistors. When you think of a transistor, just think of it like a toggle switch here with the two screws. There's the collector, there's the emitter, the toggle is the base. When the transistor's off, there's no connection between the collector and emitter. All I do is flip the transistor on by putting 7/10 of a volt on the base, and those two guys are connected together, and that's all there is to it. Very, very simple. To be quite honest with you, it doesn't make a lot of difference if you understand how a transistor works. The most important thing you can learn is how to test it to see if it's good or bad. And you'll find that that's how I'll be working things this entire class. As we go through this class, you'll see that I personally don't give a rat's ass if you know how the thing works, as long as you can fix it. And that's what we're going to be going through here. So let's take a look at the transistor test and see how we test the transistor. Turn in your blue book to page 10. In order to test the transistor, you do have to know which lead is which. You have to know which lead is the emitter, which lead is the base, and which lead is the collector. If you look at the TO3 package that I gave you, that's the big one, the TO3 package. You see that there ain't but two leads sticking out of this thing. In this particular case, they're labeled, but they aren't always labeled in all these transistors. These leads, if you hold it if you hold it right side up so you can actually see on these particular transistors, the little leads there, and the one on the left is the emitter and the one on the right is the base, right? The collector is the case of the transistor. The metal case of this transistor is the case. For that reason, whenever you see one of these transistors mounted on the side of a chassis or on a metal heat sink, and we'll talk more about heat sinks. Well, I can show you a heat sink here. Wait. Here's a couple of them, in fact. If you look on this metal thing here, this finned aluminum thing is a heat sink, it's called. Transistors don't like to run hot, and that's why they're mounted on this heat sink. Whenever you see transistors mounted on heat sinks, you'll see these insulators mounted behind them. You don't mess these up. I'm just going to pass them around so you can look at them. I only have 4 of them here, so be careful with them. These are made out of mica. They're fairly delicate, so don't screw them up. Because the collector is the case of these things, it's electrically active. It's going to have some voltage on it most of the time. Can be anywhere from 12 volts to 160, so, depending on what the circuit is, so be careful. You will always see one of these insulators mounted behind it. You'll see an insulator mounted behind it like this. When you change the transistor, you must make sure that you put the insulator back. You don't necessarily have to replace the insulator and put a new one in as long as it's intact. Also, very important word of warning. Sometimes you'll see some white goop on these things. It almost looks like the transistor leaked out some white. It looks like toothpaste, exactly like toothpaste. It doesn't taste like toothpaste. So this white goop, it did not come out of the transistor, although the transistor is filled with the same stuff. There's this stuff that they put on transistors called heat sink compound. You'll probably see it on Wednesday when we pull the power supplies apart. This heat sink compound is put on the back of the transistor and also on the heat sink, on the insulator and on the heat sink. It's used to help conduct the heat away from the transistor. It's not electrically conductive, just heat conductive, thermally conductive. Caution, warning, danger, Will Robinson. Don't get this jazz on your pants. Once it gets on your clothing, you just can't get it off. I don't know what the hell this stuff is made out of, but if you get it on your pants or something, you won't get it off. So when you get this on your hands, don't go, like this. It just, unless you don't care. If you're wearing work pants, no big deal. Might improve them, but be careful about that. When you see it, it doesn't mean that your transistor exploded or anything. That's perfectly normal. People put that stuff on. You're supposed to put new heatsink compound on whenever you change a transistor. I don't do it because I was trying to be very professional for a while, and I carried a little tube of it around in my toolbox till my long nose pliers skewered the tube and got this white crap all over my tools. I'm sure whoever stole my tools still has that white crap all over them because I couldn't get it off or shit. So anyway, so be aware of that. Now, even though it's printed like this, the way I normally think of this transistor, because you do have to know which lead is which, the way I normally look and tell which lead is which is that if you look very carefully, if you draw an imaginary line dead center in that transistor, you'll see that those leads are not right on center. They are slightly offset, aren't they? If you look at it carefully. If I hold the transistor so that the leads are slightly offset above the center line, they're in alphabetical order. Base is on the left, the collector is the case, and the emitter is on the right. That's the way I remember it. You're not going to be able to see the bottom of these transistors because they're mounted on things like this. You can't see the bottom of that transistor without taking it off, but you want to be able to test it without pulling it off. You get what I'm saying? So the only way you can tell which lead is which is look at it carefully. Those leads are not right in the middle. They're just slightly offset. And if you hold it so that they're offset above the center line, alphabetical order, base, collector, the case, and emitter. The TO220 package, extremely easy, alphabetical order. Base, collector, emitter from left to right. B, C, E. Also, very important, in the TO220 package, the center leg is connected to the metal tab on the top. These are electrically the same point, meaning that the metal tab is electrically active. It is the collector as well. And again, when we open up our power supplies, you'll see that there's an insulator behind these things as well. There's a small insulator that goes behind these transistors as well. So BCE, alphabetical order. Now, the little dinky one I gave you, unfortunately, is not standard. The TO92 package, remember this is TO220, TO3. The TO92 package changes depending on where the part was manufactured. In the United States, and this is the way you'll see it from the bottom, you're now looking at the bottom of the transistor, looking up that way. It's emitter, base, collector. That's in the USA. But depending on where it's made, it'll be a little bit different. Do not write this down what I'm about to show you because I can never remember this. One of them is BCE and the other one is ECB, and I can't remember. One of these is Japanese and the other one is European. The reason that I can't remember is that it's silkscreen on the board. The reason I can never remember is that it's silkscreened right on the board, and the board tells you which lead is which. For instance, you see here a bunch of these little transistors. You can see them all over the place. This really nice clean monitor. Well, on the bottom side of it, it tells you which lead is which. For instance, you see the little E's and B's and C's that are in the circles there? Here's transistor X304, transistor number 304. Here's the emitter lead. Here's the base lead. Here's the collector lead. You know, here's another one. They're all over the place. Here, let me show you another one. Here's X104. See E, B. Here's another transistor, emitter, base. You know, they show it to you all over the place. Here's another one. Here's X402. Looks like it's been changed or tested. Collector, base, emitter. So this is pretty simple, really. That's why I can never remember which one's which because I never have to. You know, if I don't have to memorize something, I'm sure as hell not going to do it. That's for sure. So I got enough stuff to remember anyway. But these are always the same, and these are pretty easy. Well, let me show you how to test the transistor, because then we're going to do our big transistor lab, and then we're going to go home. So just hold your horses for a second here. Let me just show you how this works first, then we'll go through it. I'll let you guys do it. And if you look at the chart on the top of page 10, this tells you how the transistor test works. And again, you're using the diode test setting of your meter. Using the diode test setting. Here's how this works. Don't do it now, just watch me. You're going to have a chance to do 40 transistors in just a few minutes, okay? Because I got this big bag of transistors here. You're going to check every one of these. Half of them are good, half of them are bad, and you'll see how this works. I start with the red meter lead on the base of the transistor, and again, you can touch your fingers to the meter leads. With the red on the base and the black on the emitter, I see a junction drop. Remember what I mean by junction drop, something usually between 0.5 and 0.9, maybe a little bit lower than that, depending on what type of meter you have. So red on the base, black on the emitter, I see 0.5. Leaving the red where it is, move the black to the collector, you should see the same thing, 0.5 in this case. It's generally the same number, or pretty damn close to it. Those are two junction drops. So far, so good. What I'm doing is I'm checking the junction between the base and emitter, and then between the base and collector. So far, so good. Then I reverse the leads. I put the black lead on the base and do the exact same test. Red on the emitter, it should be open this time. Remember how the diode showed you a junction drop one way and open the other? That's what we're doing here. Leaving the black lead on the base, moving the red lead to the collector, also it should be open. Now, final test. Remember that in a transistor, the main switch in a transistor is between the collector and the emitter. Remember that? That's where they call it the collector current. That's the main current flow in a transistor. As a final test, make absolutely certain, put one lead on the collector, the other lead on the emitter. It should be open. When you reverse the leads, collector to emitter should be open. And that's the complete test. If it fails any one of those tests, if it gives you a junction drop where you ain't supposed to have one, or doesn't give you one where you should, or you see a short circuit anywhere, if it fails any one of the 6 tests, it's bad. It'll be really obvious to you in about 5 minutes which one's bad and which ones are not. So just hold on for just a second here. It only takes about 20 seconds to test a transistor. Again, red lead on base, base to emitter, junction, base to collector, junction. Reverse the leads, black on the base, open, open, collector to emitter, open, collector to emitter, open. It's good. And again, you're gonna have a chance to do some bad ones in just a second. Not only does this test tell you if the transistor is good or bad, but the test will also tell you if the transistor is an NPN or PNP. If you happen to have an unknown transistor and you want to know what the hell's going on with it, it'll tell you if it's NPN or PNP, the two opposite polarities. If a transistor is an NPN transistor, here, I'll make this really official here. If the transistor's an NPN transistor, when you put the red meter lead on the base of the transistor, and you go from base to emitter and base to collector, you'll get the junction drop reading. NPN, the center letter is the base. The red lead is the positive lead of your meter. If you put the positive lead on the base, it conducts. On the other hand, a PNP transistor, when you have the black on the base, that's when you get your junction drop reading. And if you look at that chart, that's exactly what the chart on page 10 is showing you. What the chart on page 10 is showing you is where to put your black meter lead, where to put your red meter lead, and the reading you should get if it's NPN or PNP. You know, when you look at this guy, and you look at the chart on the top of the page, it says red lead, put the red on the base, black lead on the emitter. If it's an NPN transistor, you'll get a junction drop. If it's PNP, you'll get an open reading. And same thing all the way down. I have no idea anything about this transistor at this point. And it's true, I really don't. Identify which lead's which. I'm going to put the red lead on the base, the black on the emitter. I've got a junction drop. This looks like a good NPN transistor right now because I've got the red on the base, and that's when I get the junction drop. So far this looks like a good NPN. Leaving the red on the base, black on the collector, not touching the tape. I get a junction drop. So far it looks like a good NPN. I reverse the leads. Open, open. Looks like a good NPN to me. Final check, collector to emitter. Open, open. Number of is a good NPN transistor. That's all there is to it. When it fails, if it fails any one test, you can stop right there. If the first test you do is bad, it's bad. There's a bad one right there. Write down bad right away. Now I'm here. I'm going to circulate around you, amongst you. Okay, yeah. Start with the red on the base and the black on the emitter. You're getting a junction drop, 0.5. Leave the red exactly where it is. Don't move it. Move the black to the collector. 0.5. Same thing. So far, so good. Now,
There's 6.
leave this the way it is. Reverse the leads in your hands.
Okay.
Do the same thing you just did. This time we should get an open reading.
Yes.
Open. Open.
Good.
Now, final check. Collector to emitter. Very important. The collector, which is the case, to the emitter. Doesn't matter which lead you put where. Should be open. Now reverse your leads. Same 2 pins.
Are you done with 20?
Collector to emitter. There you go. Open. That's a good one.
You can go as fast
Okay.
as the other way.
All right.
You get
That's the base there, isn't it? Base to emitter. Open. Now look. Now let's think about this for a second. Base to emitter. This time you got the open reading, correct?
Right.
Meaning so far it looks like a good PNP, like Dan was saying. It looks like a good PNP so far, doesn't it?
Mm-hmm.
Okay, let's keep going. Leave the red where it is. Move the black to the collector. OL. So far it looks like a good PNP. Now reverse the leads in your hands. Same test. This time with the black lead on the base. Junction drop. Look, it's following. So far we got 3 that are perfect PNPs, right? Okay, leave the black where it is. Move the red to the collector. Junction drop. So far so good. That's that one. Final check, collector to emitter. Should always be open. Correct. The emitter's lead on the right. Open, which it is. Now reverse those two wires, 2 leads.
And this one, right? Which one?
Passed every one of those tests, didn't it? It's a good PNP. Cool?
Yep.
I do want to kind of go over a little bit more about how the transistor works, because when I start describing other circuits, it'll really help if you know a little bit about how the transistor works. And remember I said that the transistor is just basically just a switch. Let's look at a typical place where we might have a switch. Let's say, for example, the dome light circuit in your automobile. You open the car door and the dome light comes on. Let's look at a simplified version of that. So here's our car battery and negative ground. And remember, that's that chassis ground symbol that we looked at yesterday. And it's a 12-volt car battery. And the current would leave the battery, and presumably it would go through a fuse first. And this is the schematic symbol for a fuse. Then the current goes to the light, the dome light, the light in the roof of your car. And then it goes to the push button switch that's in the door jamb of your car. And the schematic symbol for that push button switch would look like this. and then the other side of the switch goes to ground. And as I mentioned yesterday, you can all see that by putting a ground here and a ground here, it's exactly the same as if I have a wire between the two, right? Because the ground is just the metal chassis of the car. Now, this switch, this is the switch that's in the door of the car. When you open the car door, the switch, when the door is closed, this switch is pushed in and it is not making contact there. When you open the car door, the switch retracts, doesn't it? Or goes back to its normal position, really, and that shorts these two contacts together. That completes the circuit, and the electric current, according to conventional current, according to the schematic diagram, the current will flow out the battery like this. It'll go through the fuse, through the lamp, through the switch, which is now closed. When a switch is closed, it is turned on. When it's like a closed or complete circuit. When a switch is open, it is off, like an open circuit. And then to ground, and of course the return path, we've got to have that complete path back up like that, and that's our complete circuit. Now, a couple of weird things about this thing. Number one, well, one weird thing especially. Number one, you'll notice that the switch is not in the source path, is it? The switch is in the return path. Does it make any difference where I break the current, to break the connection to turn the light off?
No.
It really doesn't. If I break it in one place, I break the current flow everywhere in the circuit. So that's pretty weird. This switch, instead of switching the source power on and off, as you'd kind of expect, switches the ground in and out. It's called a ground switch. It's called a ground switch. And this is actually the most common way to control things in electronics. When we're dealing with electronic controls, like turning light bulbs on and off, we very often use a ground switch. Instead of switching the source in and out, we simply switch the ground in and out. Pinball machines are the same way. We'll see this on Saturday. In a pinball machine, to energize the coils in the pinball machine, there's always power going to the coils. Always, continuously. The whole time the game is plugged in and turned on, there's always power to the coils. To energize the coil, they ground one side of it. The ground is switched in and out. You'll see what I'm talking about later on. I'm going to show you a lot of examples of the ground switch as we go through the class. It's very common in monitors. In most circuits, instead of switching the power on and off, we switch the ground in and out instead. It really doesn't make any difference where we break it as far as being able to turn the light bulb on and off. It's much more convenient for us to make and break the ground connection for reasons which you'll see as we go through the class. Well, let's replace the ground switch. Let's replace this mechanical switch with an electronic switch. Let's replace it with a transistor. And remember that in a transistor, the main switching action is between the collector and the emitter, like that. And then here's our return path. I won't ground it here. We'll just do it like this, just to be convenient. Now remember the way the transistor works. As long as the transistor is turned off, there is no connection at all between the collector and the emitter. And just like that open switch in the door jamb of the car, the light's not going to be on. When the transistor turns on, the collector is connected to the emitter. And of course that closes the switch and allows the current to flow through the circuit. At the moment, for the sake of this demonstration, I don't have a 12-volt battery. I've got a 6-volt battery here. So there's our 6-volt battery. Now, we know that we need a certain amount of voltage on the base of the transistor to turn it on. Remember how much it was? 0.7, right. And here I've got a battery, and the battery is 6 volts. somehow I've got to cut that 6 volts down to just 0.7. I don't want to put 6 volts on the base of this transistor. It might damage it. What part do we know of that I can use that we've already looked at that I use to cut that voltage down? Resistor, sure, absolutely. In fact, I'm going to use a potentiometer. And I'm going to connect the pot like this. One side of the pot, I'm going to connect right to the positive side of the 6-volt battery. Making a nice big long pot here. The other side of the potentiometer, I'm going to connect to the negative side. Let's just call that ground here so that we know that that's 0 volts. And the wiper, I'm going to connect to the base of the transistor. Now let's think about this for a second. If this side of the pot is hooked up right to this wire, what's the voltage going to be right there? 6 volts, isn't it? Sure, because it's hooked right up to the 6-volt battery. The voltage is the same everywhere along a wire. It's 6 volts there, it's 6 volts there. It's 6 volts right here as well, isn't it? On the top of that lamp, obviously. The other side of the battery, the other side of the potentiometer is connected to ground, as is the negative side of the battery. So what's the voltage right down here?
0.
It's got to be 0 volts. All right, now let's think about this. Suppose the wiper of the potentiometer is all the way down here at the bottom of the pot. What would the base voltage be on the transistor?
0.
Be 0, wouldn't it? I mean, look, it's actually touching ground right there. So obviously the transistor wouldn't be on. If the wiper was all the way up here at the top of the pot, what would the voltage be?
6 volts.
It'd be 6 volts, wouldn't it? That makes a lot of sense. Okay, now here, put on your thinking caps. Suppose the wiper was exactly smack dab right in the center. What do you suppose the voltage would be?
3.
Sure, of course. I mean, doesn't that make sense? It'd be 3 volts there. If it's 6 volts up here and 0 volts there, if you stick it right in the middle, it kind of makes sense that it would be exactly 3 volts. You'll notice that you didn't ask me what the value of the pot was. You never said, hey, how many ohms is that pot? And really, it actually doesn't make any difference, which is kind of a weird deal. And I won't go through why that is. But intuitively, I don't give a shit, how it works electrically speaking. Intuitively speaking, if it's 0 here and 6 there, if it's right in the middle, it's going to be 3, and that's the bottom line. Suppose the wiper is only 1/4 of the way up from the bottom. 1.5, sure. Whoops, 1.5. Sure. So obviously, the higher up we go, the more voltage we'll have on the wiper of the pot. So since we only want 0.7 or so, it's going to be down here pretty far down, isn't it? All right, now let's see how this works. And I have this demonstration circuit hooked up right now. We're going to add a meter to this thing. We're going to add a digital multimeter, and we're going to set the meter to read the base voltage of the transistor. So it's going to be on DC volts. We've got this black meter lead. Where are we going to put that? Ground, or the negative side of the battery, or something like that. And then the red wire will connect to the base of the transistor. Okay, let's see what happens here. I'm going to draw a little chart up here. Well, yeah, I guess I'll draw it up here where people can see it. And we're going to take a look at what the base voltage is doing, and this other side will be what the lamp is doing right at the time. Right now, the meter is showing me 0 volts. Here's the lamp. And the lamp is off. So right now the base is 0 volts, and the lamp is off. Let's start, and I've got this potentiometer here. Let me start increasing the base voltage. Let's see what happens. 0.1, nothing's going on. 0.2, nothing's going on. 0.3, lamp is still off. 0.4, lamp is still off. even at 0.5, right now I have half a volt on the base of the transistor. Right now the base voltage has a half a volt on it. The lamp is still off though. Remember, we need about 0.7 to turn it on, right? .6, right there's 0.6. No, lamp's still off. Oh, there we go. It's just barely starting to glow. Maybe you can't really even see it. If you stand up, you might be able to see it. At 0.66 approximately, 0.66, the lamp is just barely started to glow. It's really incredibly dim. Let's go up a little more. 0.66, 0.67. Look, it's really coming on now. 0.68, 0.69. Looks like that's about as bright as it's going to get. Right there at about 0.69 really, but let's call it 0.7 just to make it easy. In fact, that's about as high as I can make it go. Let's call that 0.7. At 0.7, the lamp is completely on now. So, as the voltage increases, even at half a volt, we've got nothing on that lamp. It takes that 0.7 or so to get it turned on. Now, remember, 0.7 is an average. The larger the device is, the less voltage it takes to turn on. I know that really seems backwards, and when I first discovered that, I thought, what's going on here? Why is that? But a larger device has more surface area on the p-n junction, and so there's more electrons cruising around, and it doesn't matter. Anyway, so at half a volt, that thing's still off. I increase it to 0.66, and it just barely starts to come on. But you'll notice just 4 hundredths of a volt later, the difference between 0.66 and 0.7 is only 4 hundredths of a volt. Now the lamp's on completely. So, in a way, when I said that a transistor is just a switch, I kind of lied to you, didn't I? Really, it is a switch in that we can make the transistor completely off, if you look at the lamp, or we can make it completely on, completely off, completely on. But we can also put it anywhere in between, anything from completely off to completely on. It's completely, continuously variable between completely off and completely on. So, in a way, a transistor is more than just a switch. It can also act like a variable resistor. I mean, if you look at this, what it's really doing is, when the transistor's turned off, and there's no connection between collector and emitter, there's really millions and millions of ohms there, right? It's like an infinite resistance. It's a tremendous amount of resistance. As the voltage on the base increases, the resistance between the collector and emitter drops, doesn't it? It gets lower and lower and lower because when the transistor is turned on completely, there's no resistance there. It's shorted together. So obviously it's going from an infinite resistance off, and as I make this thing go off, as I make this go a little bit brighter, the resistance is dropping between the collector and emitter until finally there's no resistance at all and the light's on completely. In a way, what's happened is that this change in voltage has been transferred into a change of resistance between the collector and emitter. And as a matter of fact, that's where the term transistor came from. Transistor happens to mean transfer resistor, is really how they got that term. You don't really have to know that, but that's what a transistor is. They didn't just make up the word transistor out of nowhere. That's where it came from, transfer resistor, as the change in voltage of the base is transferred into a change of resistance between the collector and the emitter. To be honest with you, it wasn't until I hooked up a transistor just like this that I really understood how transistors work. And there's really nothing mysterious about them. It's not like a transistor takes in a signal over here and then somehow processes it and spits it out over here. That isn't how it works at all, although that's what a lot of people think. A lot of people you know how a transistor is referred to as an amplifier? You know, they say like a transistor can amplify. It's not like the transistor takes a signal in and amplifies it and spits it out. All they're talking about is this, that an itty-bitty tiny change on the base, in this case just this 0.04 of a volt, can make the difference between something being, let's say, just partially on and completely on. Now, if we add another meter to this thing, we can really get a real good idea of how this thing works. I'm going to add another meter here. And I'm going to set this meter up to read the collector voltage of the transistor. Remember, the first one was reading the base. This one I'm going to connect to the collector of the transistor. Here's what's happening right now. The base voltage is 0 volts. The meter on the left is the base. The meter on the right is the collector voltage. You notice the collector voltage is up around 6 volts. Let's watch what happens as I increase the base voltage. And what we're looking at is the lamp, the base voltage, and the collector voltage. All right. Let's start to increase the base voltage. 0.1, 0.2, 0.3, nothing's going on. Nothing's happening. Now look, right here, let me back it down a little bit. At about 0.5, watch the collector voltage. It's going to start to drop now. See the collector voltage start to drop? 4 volts now. You see how the lamp's a little bit dim? It's starting to come on now. The base voltage is going up. The collector voltage is dropping. For instance, yeah, fast. Right now we have, we've got the devil on the meter on the left, 0.666 on the left, and the meter on the right, the collector voltage, is showing 3 volts. The light is now real dim. And here's why. What's happening right now at 0.66 on the base, the light was dim. The light was dim because, if you remember, the collector voltage is only 3 volts now. The collector is not completely shorted to the emitter. It's not going all the way down to ground. There's still some resistance here. As a matter of fact, if I have 3 volts here and 6 volts here, the resistance of the transistor must be exactly the same as the resistance of the lamp. It forms what we call a voltage divider. And you don't really have to know that right now. But the lamp is dim because it's a 6-volt light bulb. I have 6 volts on one side, 3 volts on the other. What's the actual voltage across the lamp? 3 volts, sure. It's only 3 volts. No, 6 minus 3 is 3, not 4. Okay. See here, 6 minus 1, 2, 3. Okay, 3 volts left. Anyway, so it's a 6-volt bulb, but only 3 volts are across it. So that's why we see what we see. Let's see if I can turn this back on now.
I flipped over that one.
There we go. So here we go again. And watch what happens now. As I increase that base voltage just a little bit, that collector voltage drops like a rock. I mean, the base voltage is only moving up by thousandths at a time, and look at the collector voltage drop like a rock until it can never go all the way down to 0. There's always a tiny amount of voltage left. In this case, about 1/10 of a volt, well, 0.16. The collector can never completely short to the emitter. There's always a tiny amount of voltage that's left. It's what the hotshot engineers refer to as, and you don't have to know this, V, the voltage from the collector to emitter, V sub CE. You don't have to know that, though. But for all intents and purposes, as far as we're concerned, it's shorted together. And now we have essentially 0 volts on the collector because it's shorted right to here. 6 volts on the other side of the lamp, and so the lamp's on all the way. So as the base voltage goes up, what happens to the collector voltage? It drops, right? The collector voltage goes down. Okay. And this is how a transistor works. This is all there is to a transistor. There's nothing mysterious or weird about a transistor whatsoever. That's all it does. You stick enough voltage on the base, and the collector and the emitter are connected together. Now this is an NPN transistor. The PNP transistors works basically the same way. There's just one slight difference between them. First of all, when I said that it takes 7/10 of a volt, this is an NPN transistor. When I said it takes 7/10 of a volt on the base to turn the transistor on, I lied. It does in some cases, and in this case it did, but in actual fact the base of the transistor is really stupid. The base of the transistor doesn't really know what you're putting on it until it compares itself to the emitter. In order to get an NPN transistor to turn on, the base voltage has to be 7/10 of a volt higher than the voltage at the emitter. The base really compares itself to the emitter. In order to get that NPN transistor to turn on, the base has to be 7/10 of a volt higher than the voltage on the emitter. Now, in the circuit we just looked at, the emitter was grounded, making it 0 volts, and 7/10 definitely turned it on. I mean, we can see it. It's right there on the meter, 7/10 of a volt. You know, right there on that meter for those of you at home. And that's fine, but it won't always be like that. For instance, we'll look at some circuits, perhaps today, perhaps first thing tomorrow morning, where we'll have an NPN transistor, and the emitter will have 12.7 volts on it. I'm sorry, 12 volts on it. To get that transistor to turn on, we put 12.7 on the base. We'll look when we look at monitors on Thursday, 120 volts on the emitter, 120.7 on the base. The base is really stupid. It's like you put voltage on the base and it goes 120.7. Oh, I don't know. Let me look at the emitter. Oh, 120. Okay, I'll turn on. You know, it just doesn't know, you know, what its voltage is at all. It has to look at the emitter, and as long as the base is 7/10 of a volt higher than the emitter, the transistor turns on. That's for an NPN. The PNP, the base has to be 7/10 of a volt less than the emitter. 7/10 of a volt more negative. That center letter is the base. If it says N, then it's got to be more negative. So for instance, if I were to use a PNP transistor for the same circuit to light up the lamp, just a demonstration circuit, I would actually have to connect it like this. I couldn't do a ground switch deal. I would have to connect it like this. 6-volt battery. How much voltage would I have to put on the base of the transistor to turn it on? 5.3 volts. That's right. Very good. There you go. That's 5.3 volts, sure. 7/10 of a volt less than the emitter. What's the emitter voltage here? 6 volts. Gotta be, huh? It's hooked right up to the battery. The base is 7/10 of a volt less. In this case, 5.3 volts would turn the transistor on. Now notice also the way the current flows through the transistor. Following the arrows from positive to negative, notice it follows the arrows. See that? Follows the arrow from emitter to collector, and then back up again. In the NPN circuit that we just looked at, same thing. Well, no, it still follows the arrow. We had the lamp first. See? Same thing. The current still flows following the arrows. So that's if you ever want to trace current flow through transistors and stuff, that's how you do it. The current you just follow the arrow from the collector to the emitter, which is the main current path of the whole transistor. Make sense? Any questions so far? Pretty dang simple, huh? Well, you know, to be honest with you, if you don't remember how transistors work, it's really perfectly okay, because as long as you know how to test it, that's the most important thing. And naturally, as I go through the class and we look at more and more circuits using transistors, I'll explain again and again how the thing works. But even if you don't get it at all, you really, the most important thing is you just have to know how to test them. That's the main deal. Well, let's say you've tested the transistor and you find it to be bad, and now you have to come up with a replacement part. You have to come up with a substitution part. It's not always real easy to find the exact right transistor. Turn in your blue book. Let's look at page R7, I think it is, or maybe R8. It's on transistors here. R7. R7 is the one, and that's the TO3 package. Shows you a little picture of the TO3 package up here. Like the one that I gave you. Transistors have basically the same specifications as diodes do. That is, they're rated by voltage and current. The voltage rating of a transistor is exactly the same thing as the voltage rating of a diode. It's not how much it puts out, it's the maximum it can handle. You know, if I have a 100-volt transistor, I can use it in any circuit up to 100 volts. I can use it in a 5-volt circuit. I can use it in a 10-volt circuit. I can use it in a 99-volt circuit, but I can't use it in a 150-volt circuit. Remember that in the diode, we called the voltage rating the PRV, the peak reverse voltage, or PIV. Remember that? We have yet another name for the voltage rating of a transistor. Now, there are actually many different voltage ratings for transistors. There's only one that we really care about as far as we're concerned. And it's known as V for voltage sub CEO. Remember, these little letters here are called subscripts. Subscript. And they further describe what we mean by the big letter. In other words, V, obviously, this is the voltage rating. It's the voltage rating from the collector to emitter when the base is open. That's what that O means. Well, if the base is open, is the transistor on or off?
Off.
It's off, right? Oh, good, Mel. There you go. Sure. If the base is open, the transistor's turned off. So if you want to, you can think of that as meaning off. The voltage from collector to emitter when the transistor's turned off. But of course, that's when the transistor is blocking the voltage, isn't it? When it's turned off, that's when it's blocking it and it's not allowing it to flow. Sometimes you'll see this listed as BV for breakdown voltage. V sub CEO, BV sub CEO, same thing. This is the voltage rating, the main voltage rating of the transistor. Number 2, current. Remember, we use the letter I for current. In this case, it's called I sub C, the collector current. Remember, that's what they call the main current flow in a transistor. The current that flows from collector to emitter is called I sub C, the collector current, the main current flow in the transistor. And the current rating of a transistor is exactly the same as a diode. It's the maximum amount of current that you can put through the transistor from collector to emitter without it burning up. And of course, physically, the larger it is, the more current it can handle. Substituting transistors is exactly the same as substituting diodes. If you have a transistor and you need to get a replacement for it, you can always use a transistor of the same or higher voltage or current ratings. Always. You can go up as high as you want in voltage, you can go up as high as you want in current. All transistors work exactly the same way. The only difference is these ratings. But there's one more weird specification for transistors that you got to know about. And it's something known as the gain of the transistor. Also referred to as the beta, B-E-T-A. The gain of the transistor is the transistor's ability to amplify. And I'm going to kind of lie to you at first and tell you something that's not exactly perfectly true, but I'll clarify it later, just to make it convenient for you. You know how, when we were doing this experiment over here, the tiniest change in voltage on the base produce this much larger change on the collector. You know, just, well, like we went, you know, at 0.66, the thing was dim, but at 0.7, just 400 volts later, it was up full bright, and we had the collector drop to 0 volts. It only takes a fraction of a volt change on the base to produce a much larger change between the collector and the emitter. Remember when we did the experiment, just 0.04 of a volt change on the base produced a 3 volt change on the collector, didn't it? Remember that from just a few minutes ago? Well, that's kind of what we're talking about, although not really. It really has to do with the amount of current, not voltage, but I'll tell you more about that later on. Anyway, what gain is how itty-bitty of a change on the base will produce how big of a change on the collector, basically. How sensitive is the transistor? Well, let's look at the transistor that you have here. Let's look at the 2N3055. It's the big transistor that I gave you. Yeah.
Randy,
Yeah.
I have one of those because I turned it in last night with all the other.
You accidentally turned it in?
Yeah.
Yeah, I'll give it to you in a second. You don't have to look for it. You don't have to look at it to do this. The big transistor that I gave you, if you look at the part number on it, it says 2N3055. This is a really common transistor. It's probably one of the most common transistors in the world, actually. So let's look it up on the chart on page R7. As a matter of fact, well, here, I'll give this to you, Claude, because if you can conveniently pull out your transistor, I do want you to look at it, actually. I think you just sold the other one. Okay, do you see the part number on it, 2N3055?
Yeah.
Remember, the 2 is the number of PN junctions. Remember that? I mentioned that yesterday. The N just means it's a semiconductor. The number, you can't tell anything about the specifications by the number. It's just a number. You got to look it up. There's another number on your part. What's that other number? 9148. That ain't the part number, teen guys and gals. That 9148 is the date code. It's when it was manufactured. It was manufactured on the 48th week of 1981. 91, sorry.
91.
Sorry. God, I guess so. The 48th week of 1991. Meaning, somewhere around the beginning of December. Be careful about this. Almost every part has a date code on it, in addition to the part number. So, if you see a number that's the last 2 digits are 52 or less, and the first 2 digits look like a year, you're not looking at the part number. Every now and then I get this call from somebody, Randy, I'm trying to find this transistor. Yeah, what's the part number? It's a 9016. Oh, no such transistor. Yeah, man, I'm looking at it right here. God damn it, it's a 9016. No, that's a date code. The reason they put date codes on there, it's not like milk, where it'll go bad. The reason they put date codes on is if they have a bad run of parts, like, something happened, all the parts are failing for that week, they can recall that one production. It's like you hear every now in the news, recalling Tylenol lot number GB6X503 or whatever it is, same kind of deal. It's just an indicator so they know which batch this transistor came from in case they have a recall and they got to recall them. Otherwise, they'd have to recall them all. So be aware of that. That's not the part number. And you'll see that same date code on integrated circuits as well. So be aware of that. So let's find that 2N3055, and if you look at your chart on page R7, there's obviously 2 charts here. On the very top of the right-hand side, you see under device type, do you see NPN 2N3055 right there on the top? Right next to it under PNP, it says MJ2955. This is the same part with the same specifications, same voltage, current, and all that stuff, but opposite polarity. It's PNP instead of NPN. It's called a complementary pair. You don't really have to know that, but it's called a complementary pair. Two transistors with the exact same specifications, but opposite polarities. They are not interchangeable in any way. You can never interchange an NPN for a PNP under any circumstances, no way, no how, nowhere. All right? But we use complementary pairs occasionally. For instance, in a jukebox amplifier, there's usually two output transistors for each channel, left and right. Those are almost always complementary pairs. One's NPN, one's PNP. It's what they commonly call a push-pull circuit. You don't really have to know that either. But two transistors, same specs, opposite polarity. They're not interchangeable. Well, let's take a look at the specifications here for the 2N3055. On the far left-hand column is the current rating. What's the current rating of this transistor?
15 amps.
So it's a 15 amp transistor. In fact, let me just write this in red so that we can easily see it. It's a 15 amp transistor, meaning it can handle anything up to 15 amps. The next column over is V sub CEO, the voltage rating, which is what? 60 volts. So this is a 60 volt, 15 amp transistor. It can handle anything up to 15 amps, anything up to 60 volts. And then if you look over here under the gain, HFE is the gain. The gain is abbreviated H sub FE. I don't know, I have no idea what that actually stands for. And what is the gain of this transistor? It's 20/70.